In this video, we will be learning about the heat treatment. So let's start. So what is heat treatment? Basically, heat treatment is the combination of heating and cooling operations which are timed and that is applied to a metal or an alloy in the solid state in a way that will produce the desired properties. So if we want that a desired properties, if we want a desired microstructure in our metal or alloy, we apply certain heat treatment processes in which we heat the material, we hold the material, and then we cool the material with different rates. Okay, so for steel, if we are discussing the steel case, so we will be talking about the region of austenite. So we'll be heating our material to the austenitic region, and then we'll be cooling it down to with certain rates, okay, with certain time. So let's move on. So what this is a particularly this is a heat treatment cycle in which you can see that we heat the material, we heat the alloy to a certain temperature. On the x-axis we'll be having the temperature, and on the y-axis we'll be having the time. So we are heating the material to a certain temperature. For example, we are heating the material to 500 degrees Celsius, and then we are holding, we call it holding or we call it soaking. So we allow the material to soak the temperature homogeneously, so the material completely uh, now has the same temperature from the surface to the core, and we hold it, and then we cool it down with a certain rate. Either it is the same as the heating rate, or it may be different from the heating rate, the cooling rate. Okay, so that is called cooling, or that is called controlled cooling. Okay, so this is another type of heat treatment cycles which you can see, which in which you can see that there is temperature on the y-axis and time in the x-axis. So you can see that we heat our material to a certain temperature, either it is 720, either it is 880, and these are two different cases, and on two different occasions it has been done. So the holding time is of 90 minutes, and then there is the controlled cooling, which has the same rate as that of the heating in this case. Then we have another example in which our material is heated to 810 degrees Celsius and hold it for 90 minutes, and then uh, we have cooled it. And in the third case, in the fourth case, we have heated it up to 630 degrees Celsius, and then we have hold it, and further we have cooled it down. Okay, so again you can see that this is the heat treatment cycle for only one of the alloy, or you can say metal. So we have heated the alloy to a certain temperature, then we have suddenly cooled it down with a very fast rate, and then we are heating it with certain intervals. You can see that we are providing a certain soaking temperatures in order to that the inclusions present in that must be homogenized, and the structure is also rearranging while we are holding it to this temperature, and then we are suddenly cooling it down in air or in the oil. Again we are holding it to a certain temperature, and then we are cooling it down, and then we are tempering it. We are providing multiple heat treatment cycles to a material, which is called tempering, which we'll be studying in the later slides. So it was just an intro of the heat treatment cycles. We'll be discussing the cycles for each heat treatment process. So you know that up till now you know that we have three stages in the heat treatment. One is of the heating, in which we ensure that the temperature we want is achieved uniformly, and then the other stage, the second stage, is of soaking stage or holding stage, we can say, in that the metal at a particular temperature is given some time so that it soaks the temperature homogeneously, and in the third stage we cool the metal towards room temperature or to any temperature if we want to hold it down further. So there are a lot of types of heat treatment processes, but some I have some common, very common and very general I have mentioned here, which is annealing, number one. Secondly, normalizing. Third is quenching. Fourth is tempering, and the fifth one is hardening. Okay. So basically, these are three general types of heat treatment processes, which is annealing, normalizing, and quenching. Okay. So quenching is somehow followed by tempering. Okay. So annealing. So basically, what is the purpose of annealing? First of all, it is an extreme slow cooling phenomena, and the purpose of annealing is refinement of grains. If we have a very complex geometry of grains, or if we have elongated grains, or if we have dendritic grains, as we studied in the starting lectures of this lecture series. So if we want to refine the grains, or if we want to recrystallize our material, we'll be doing annealing. This annealing also induces softness. We know that after cold working, the strength of the material is very much increased due to strain hardening. So if we want to increase the ductility now, or if you want to reduce the strength and increase some of the toughness, we'll be doing annealing. Then annealing also improves machinability. If our material is too hard, then it will be broken. The chances are it could be failed while machining. So if we want to improve the machinability, so we'll be using we'll be doing annealing as well, and to induce ductility as I discussed, and to relieve internal stresses, which are very commonly achieved while cold working. Okay. So annealing makes metal soft as possible. Okay. So we do annealing for both hypoeutectoid steel and for hypereutectoid steel. So for hypoeutectoid steel, less than 0.83% carbon, which is again as we discussed in the lecture of iron carbon diagrams, are heated above the upper critical line. So basically this is the lower critical line. Okay, and this is the these are the two above upper critical lines. Okay, so for hypoeutectoid seals, what we are doing is we have to heat the material to above the critical to above the upper critical line in order to achieve the austenitic temperature. And for hypereutectoid seals, we just heat it below the uh, upper critical line. So we are only going with the austenitic and the cementite region, and then we are cooling it down. Okay, so you have to remember this, that for uh, annealing hypoeutectoid seals, we are going above the upper critical line, which is this line in the austenitic region, and for hypereutectoid steels, we'll be only heating the material above 723 degrees centigrade, which is the eutectoid temperature, and below this upper critical line. Okay, so moving forward, what is process annealing and what is spheroidizing? So basically, process annealing is done in low carbon steels, and it may harden through cold working. They can be heated to around 100 degrees below the lower critical temperature, soaked and allowed to cool in air. So process annealing is done below the lower critical line, which is this line. So in process annealing, what happens is when we are cold working, our strength of the material is very high, and due to strain hardening and due to excessive plastic deformation. So in order to release the stresses, or in order to regain the ductility, what we do is we heat the material just below the lower critical line, just below 100 degrees centigrade, below the lower critical line, in low carbon steel especially, and we cool it down in air in order to regain the ductility and continue our core working processes. Okay, and for spheroidizing, high carbon steels may be annealed just below the lower critical line to improve the machinability. So if we have high carbon steel, so you know that the percentage of carbon always increases the strength of the material, and increases the hardness as well. Okay, so what is happening is, in a high carbon steel, uh, we'll be again we'll be heating the material to the just below the lower critical temperature in order to improve the machinability. Otherwise our material would be so hard that it will be broken down while machining. Okay, or it might crack. So then we have stress relieving annealing as well, if our material is very highly stressed and it's of low carbon steel. So as discussed earlier in the previous slide, what we'll do is we'll just heat the material, heat the steel. If it's the low carbon steel, which is the hypoelectrolyte steel, we'll be heating the material to above critical line, and then we'll be cooling it down very slowly. uh, Usually the cooling process is carried out in the furnace, and it is also controlled, and it is usually the same as that of the heating rate. Okay, so sometimes the air cooling is also uh, avoided in annealing, and furnace cooling is is required. Okay, so you can see that here is the microstructure of annealed and spheroidized steels. You can see that in a high carbon steel, the spheroids or the spheroidized cementite and the ferrite matrix. So the base, basically the light background, has the ferrite matrix, and you can see these spheroids, these small sphericals. These are called spheroids. So these are very hard materials. So if so while annealing a high carbon steel, uh, what we are doing is we are doing spheroidizing. Okay, we are forming some spheroids, which is a type of annealing, basically. So in this you can see this cementite spheroids are in circular form, or are blunt, are not sharp. So if they were sharp, so the strength again and the hardness of this material would remain the same, and also they might initiate the cracks in the final product due to these sharp uh, cementite, you can say, structures, the grains. But however, spheroids are formed while annealing the high carbon steel, that is called spheroidizing. Okay, and if you are discussing the low carbon steels or the hypoelectrolyte steels, you can see that the stresses are relieved. The elongated grains, which we discussed in the initial lectures of plaster deformation, in which you observed that these grains were elongated after the cold working, are now uh, uh, have these grains have regained their uh, structure and now are stable. Okay, with a coarse size. Okay, and this material can now further be used for more plastic deformation. Okay, then we have normalizing. So in normalizing is also a heat treatment process in which internal stresses caused by rolling or forging are removed. Again, the same I was talking about in the core working. So steels are heated above the upper critical line, soaked and cooled in air. The cooling rate is faster than annealing, giving us smaller grains. Okay, so we are not getting these coarse grains as we saw in the annealed microstructure, but we'll be getting some fine grains. We'll be getting, the size of the grain would be somewhat smaller. Okay, and normalized steels are harder than annealed ones because the cooling rate is very fast, and the grain size is also smaller than that of the annealed structure, and stress relieving. Okay, so Stress relieving the components is reheated and held at a temperature for a period of time and cooled slowly. So there is stress relieving normalizing as well. So this is the difference between the structure, the lamellar structure of the eutectoid steel. You can see that the grain size of the lamellars is very much coarser, and the grain size of the normalized structure is very fine. You can see very fine line. The distance between the cementite and ferrite lamellars is also very less in the normalized structure. Okay. So again, if we are discussed with the iron carbon diagram, here you can see that uh, here you can see that for normalizing, what we'll do is you'll just go to the upper critical line and then cool it down. Which you can cool it down in the air, or we can cool it down in oil as well. Okay, but the rate of cooling would be faster than that of the annealing. Okay, so now we have quenching. So what we do in quenching is just we just heat our material, we soak it down to a temperature whatever we require, and then we suddenly cool it down with a very fast rate. So we get a structure which is called martensitic structure. Okay, so a martensitic structure is very hard, and uh, the heat is not completely diffused out in that structure. So that is also called a diffusionless transformation. uh, and the BCC structure uh, of the of the you can say of the ferrite is now converted into the BCT structure. So we'll also be discussing that. So this is basically quenching, in which we suddenly cool our material with a very high rate to induce hardness. Okay, and then again to release that stresses from hardness, or to eliminate brittleness, what we do is we heat it to a certain temperature below the lower critical line, soak it for some time, and then we cool it down with a slower rate. So so by that we can achieve a combination of hardness and softness in our material. Okay, so this is what I was talking about, that that austenite has an FCC structure and ferrite has a BCC structure, but martensite has a BCT structure that is called body centered tetragonal. So this is due to a diffusionless transformation, and this is the hardest part in a metastate, and this is a metastable state. It's not uh, equilibrium state as well. So what is happening if we see the iron carbon diagram? You can see it over here. Uh, Hold on. Okay, so this is the iron carbon diagram. You can see that this region is the austenitic region. This is the austenite plus alpha region, and this is the alpha plus cementite region. This is the ferrite region. So if you are heating this ferrite region to the austenitic phase, so you know that the ferrite phase and this phase is the BCC. This phase has a BCC structure. Okay, and the austenite phase has an FCC structure. So if you directly cool it down from FCC to BCC, it does not become BCC anymore, but it becomes BCT in fact, because of the carbon molecule. This is the carbon molecule in this case is the interstitial impurity. Has the size of the carbon atom is very lesser than that of the iron molecule, and it gets stuck in between the BCC structure. So what happens is the length of the BCC structure, the cubic structure is increases. So these two length and breadths are equal. This A and B are equal, but the third part, the height, the C is now increased in the length because of this carbon atom stuck in between that. So that so this becomes the body center tetragonal, and this is the structure of martensite, which is the hardest, uh, uh, you can say phase, you can say the metastable phase, uh, uh, while quenching. So in order to remove the brittleness that is achieved from the hardened martensite structure, and the hardened steel, tempering is used. We use tempering in order to remove the brittleness, in order to regain the ductility and the toughness. So the metal is heated again to a certain range of temperature, that is about 220 to 300 degrees Celsius, and then it is further cooled with a very slow rate. Okay, so you can see that when hardness is decreasing of the martensitic structure, the toughness is eventually increasing. Okay, you can see that this is the hardness scale. The hardness is increasing and the toughness is increasing while we heat it to a certain temperature. This temperature is given in Fahrenheit. Okay, so this is a summary of the heat treatments which is normalizing. In A, we go above the upper critical line. For annealing, we usually are above the upper critical line, and for hyperrotatoid steels, we usually heat the material below the upper critical line and above the lower critical line. But usually, we for process annealing and for spheroidizing, we are somewhat below the lower critical line, which is this line. This is the A1 line, this is the A3 line, and this is the ACM line. Okay, and for spheroidizing, as I discussed, for tempering, what we do is we always are very much below um, the lower critical line. Okay, so you all know this is just a revision for the iron carbon diagram. This is the austenitic phase, the liquid phase, the austenite plus liquid phase, the liquid phase, the austenite plus cementite phase, and this one is the alpha plus austenitic phase, and this is the ferrite plus cementite pearlite phase. So we'll be just focusing on this region below 2% of carbon, if we are talking about the heat treatment of steels, and the the portion of concern or the phase of concern in steels would be austenite, ferrite, and cementite, from which we'll be doing uh, annealing, normalizing, and quenching. All right. So again, you can see that this lower critical line is called A1 line, this upper critical line is called A3 line, and this uh, upper critical line for the hyperrotatoid phase is called the ACM line. All right. So you can see the structures as well. Again, these are the same structures as they were discussed in the previous video lecture of iron carbon diagram. You can see the proeutectoid phases of ferrite and cementite in case of hypereutectoid, and the eutectoid composition does not have any proeutectoid phases. So now we have the isothermal transformation diagram, or we can say it the time temperature transformation TTT diagram. So what does it tell us? It basically tells us the starting of the transformation from one state to another, and ending of the transformation from one state to another, from one phase to another. So the red line you see on the first of all, on the y-axis we have temperature, and on the x-axis we have the logarithm of time, or we can say this we have time. Okay, so to the left side of uh, this red line, what we have is the austenitic phase, and the right of the this green line we have the pearlitic phase, the bainitic phase, and the martensitic phase. Okay, So we are getting certain phases, and this is while cooling we'll be getting certain phases. So how this diagram is being made? So what we do is we do some practicals. Okay, we have certain compositions in which 100% martensite is converting into 100% austenite is converting into 100% martensite. Then 95% austenite and 5% perlite is converting into 95 of martensite and 5% of perlite. And these are certain compositions in which we are heating the material to a certain time, for 30 seconds, for 6 hours, for 18 hours, for 21 hours, and it goes on. And we cool it down, some to the molten bath of certain degree Fahrenheit, or some to the cold water. So we are doing annealing, we are doing quenching, and we are doing normalizing as well. So we are doing all of this practically, and after this we achieve this TTT diagram. So you can see that the percentage of austenite transformed to perlite. So while we are transforming uh, the austenite to perlite, so this amount of time is being taken, and the temperatures would be the differentials on the y-axis, which I have not shown you, but we'll be achieving this diagram. Okay, this type of diagram. So this is the beginning of the transformation, and this is the metastable state in between, and this is the completion of uh, the transformation. Okay, so from this diagram you will be completely understanding uh, the phases which should be present. So let's assume that this region is all the austenite, which is a metastable state, which tends to convert itself into three phases, that is perlite first of all, then bainite, and then martensite. It depends on the cooling rate, that what cooling rate would get you what type of the end product. So if you are in this region at this temperature, uh, the temperature, let's see of this, let's see this diagram. So if we are above 550 degrees centigrade, and let's suppose you are at 700 degrees centigrade, so here your transformation is has started, and now this would convert into uh, the coarse perlite. And if you are below 600 and above 550, so if you are starting the transformation from austenite is starting from here, this region would have the austenite and perlite, and you can say that the structure you'll be getting over here would be very fine perlite. So the cooling rate of these two differ. This has a very slow cooling rate, uh, which in which you'll be getting a coarse perlite, and with a higher cooling rate you'll be getting a fine perlite, which will have small grains and fine grains, and the coarser one would have usually larger grains, or you can say coarser grains. So we are talking this for the eutectoid composition again, which is zero point 0.8, or in some books it is 0.76. Now if we want bainite, okay, bainite is also a structure which is very much desirable, and it's very difficult to achieve uh, while heat treatment. So if we want to achieve bainite, what we'll do is we'll be just uh, taking a temperature above below 550, above 500, okay, and then holding it for a very small amount of time, and then suddenly cooling it. So we'll be getting an upper bainite, and we'll be getting a similarly we'll be getting a lower bainite if we cool it from this region around 300 to 400 region. Okay, so we'll be getting a lower bainite. Now if we want to achieve a martensite, you know that these two transformations, the perlitic transformation and the bainitic transformation, uh, uh, are achieved from diffusion. Okay, there is a metastable state over here, you can see. This region is of austenite and bainite, and this region is of austenite and pearlite. Similarly, you can see in the above diagram that in this region above this line, this is about 550 degrees centigrade. This line is of this region contains the austenitic and the pearlitic, both the regions. Okay, and this region contains the bainitic region, the austenitic plus the bainite, both phases, which will give us the upper bainite and lower bainite, and similarly the coarse pearlite and the fine pearlite. Okay, but for martensite, the process would be diffusionless. Okay, so we after heating the material to the austenitic phase, what we'll be doing is that we'll be suddenly cooling it down in order to gain the martensite. We do not have to wait for a certain time in order uh, that if we wait for a certain amount of time, for example, if we wait around let's suppose like 30 minutes, okay, and then if we cool it down, we won't be getting the martensite directly. We'll be having this upper bainite region, or we'll be having this fine pearlite region. So we'll be getting the transformation will be diffusion, will be with diffusion of the material of the carbon atoms, and we'll be getting a fine pearlite region, or we'll be getting a upper bainite phase. We won't be getting a martensitic temperature. Martensitic phase. So in order to get a martensitic phase, what we want to do is we want to suddenly cool it down, and we want to avoid this region. We want to avoid uh, uh, the weight. We want to uh, cool it down very quickly. Okay, on a very faster rate. For example, if you are getting the perlite on a rate of 10 degrees per minute, or let's suppose 5 degrees per minute, so for martensite you will be wanting to have the cooling rate of 150 degrees per minute, or you can say 200 or 250 degrees centigrade per minute, in order to achieve the proper martensite. So this is the the start martensitic start temperature. You can see that this is around 300 degrees Celsius, and the martensitic finish temperature is around 100 degrees Celsius. It's below, in fact, the 100 degrees Celsius. Okay, so by this you can get the martensite. Or but if you cool it down to 200 degrees centigrade and then soak it, so you can also get martensite and bainite. Okay, so there is one a very important heat treatment process which is called tempering, in which we are heating the material to the austenitic phase and then holding it below the pearlitic region and above the martensitic start temperature, and then holding it down in order to get the bainite. Okay, so we'll be getting the bainite, and then we'll be uh, further cooling it down with a certain cooling rate. So let's discuss bainite. Bainite is also a unique phase. So the Ost tempering is a process in which we can achieve a phase called bainite. Bainite also refers to the mixture of ferrite and carbide. Okay, unlike the pearlite, it will also have the ferrite and carbide, but not cementite. The ferrite and carbide mixture has basic difference with respect to pearlite. Okay, the structure will not be lamellar. Okay, the bainitic structure will not be lamellar in nature, and the distribution of carbon is on a finer scale. Okay, so for example, I'll just draw it for you. If you have the pearlitic structures, you have uh, arrangement like these. Okay, these are lamellars of ferrite and cementite. However, in bainite, the carbon atoms are diffused like this. Okay, it's very fine. The distribution of carbon atoms is very fine. So this phase gives us a very unique property of strength due to these carbon atoms, and with an appropriate amount of toughness and ductility too, because it has a softer phase, it has a softer matrix phase as well. Okay, so Bainite cannot be produced by continuous cooling. It can be formed by cooling austenite at a very high rate. Okay, so we have to for Bainite we have to cool towards the austenite very on a very higher rate, and then so a transformation to perlite is suppressed. Okay, so there won't be any perlitic transformation. Then the austenite is held to a Bainite region, and then it is further cooled. So the Bainitic structure lies between the perlite and martensite. Its properties are also intermediate of both perlite and martensite. So you will be getting a very good combination of properties of that of perlite as well as of martensite. Martensite is the hardest phase, and perlite is the, you can say, is the software phase as compared to martensite. And the Bainite phase will you will be getting the intermediate properties. So as I was discussing that you will be heating your material to uh, uh, let me erase this. You will be heating your material on a very faster rate. Okay, and then you will be holding it, then you will be cooling it down. You should avoid this perlitic region, and then you will be holding it down in the Bainite region, and then you will be cooling it. So in order to gain the Bainite, what you will do is you will be heating it, you will be holding it, you will be just avoiding this neck region. This is called the neck region, okay, of the perlighting and on the Bainitic uh, region. This is the difference, and this is the neck. So you have to avoid this neck also for the Bainite and also for the martensitic transformations. All right. So this is the same diagram as we discussed earlier. So this is a summary of the heat treatment processes. So if you want to have a palatic structure, or if you want to have a coarse or fine palatic structure, or the palatic phase, you can say. So what you'll do is you'll just heat your material and cool it down. uh, you'll be choosing your transformation temperatures of this will be on this point your transformation will be start, and at this point you'll be getting a fine perlite, at this point you'll be getting a coarse perlite. Similarly, uh, at below this neck you will be getting the upper Bainite and the lower Bainite phase, and on a very sudden cooling, on a very fast cooling, you can say, you want to quench it in water and oil, you will be getting a martensitic phase, which is very hard. Okay, so basically this is a transformation from austenite to perlite. We know this perlitic structure. This is the lamellar structure of alpha and cementite, and this is Bainite. You can see that you don't see these lamellars anymore, but you can see these small, fine carbides in a ferrite matrix. And for martensite, you can see that this is a diffusionless phase. So you can see some of the uh, some of the alternate layers, but these are not all. Okay, the carbon is not properly diffused in the ferrite matrix in this case, and you cannot see the carbon stuck because that is in the lattice. But however, this would have a BCT structure. FCC uh, would be converting should be converting into the BCC structure, but due to the diffusionless process, due to the diffusionless transformation, the carbon does not diffuse out, and it gets stuck in between the lattice of iron, and so a martensitic structure, which is BCT, body tetracenter body centered tetragonal structure, is achieved. Okay, in which one dimension of the cuboid is different from the other two. All right. So this was all about the heat treatment processes. uh, Thank you.